Hi, I'm Amir Hossein Mirzabozorg, and in this video I wanna talk about moving load in Abaqus Part 2, dynamic explicit versus dynamic implicit with applying filter. This is the table of content of this tutorial. How to ask your video-related questions. Don't hesitate to ask any questions you might have about the explanations presented in this video using the comments below. We will try to answer all questions regarding the video details in the comments below. New Abaqus users who want to develop their modeling skills faster in their projects can request user-oriented online and offline services. Subsequently, we offer step-by-step guidance, tutoring, and consultancy regarding their problems. The online service includes online sessions, and the offline service includes creating special tutorials. In addition, a combination of the two can be requested. 50% discount codes are announced on our Abaqus Telegram channel and official LinkedIn page. Their links are provided in the description below the tutorial. Also, here is the link to the preview of the comprehensive Abaqus package. It includes 39 hours of instruction. Abaqus has wide usage in the modeling and simulation of structures under moving loads. There are two general methods for modeling of moving loads in Abaqus: using DLOAD and VDLOAD subroutines, without using subroutines. This tutorial explains how to use both Abaqus structural solvers to define moving loads without using subroutines. Finally, the results of both simulations will be compared. Filters implemented in the visualization module will be used to filter the results for better illustration and investigation. For defining moving loads in Abaqus, we can use each of the Abaqus standard or Abaqus explicit solvers. If you want to use the Abaqus standard solver, you must select the dynamic implicit step, and if you want to use the Abaqus explicit solver, you must select the dynamic explicit step. And both of them can account for damping and viscoelastic behaviors. Also, here is the link to the first part of the moving load analysis using Abaqus. Now I want to talk about reference paper. This paper explains how to model the moving loads applied by a moving train to the railway using Abaqus explicit solver without the VDLOAD subroutine. Here, as you can see, the weight of the train is divided between its wheels. Each wheel is modeled as a small rigid box that moves along the railway at the speed of the train. The size of the small rigid boxes is not mentioned in the paper. They are only used to model the point of effect of each moving load, so having the size equal to the size of wheels is not generally important. Here, as you can see, infinite elements are defined on each face of the model, except the top face to absorb the mechanical waves induced by the moving train to the ground. The same element type is used for both the implicit and explicit procedures. If the infinite elements are not defined on each face of the model, the mechanical waves will be reflected from these faces, leading to unreasonable results. Also here, as you can see, mesh transition zones are defined between the region underneath the railway and the far fields of the model to decrease the number of elements, leading to an efficient simulation. Tetrahedral elements are used in these regions using the free meshing method. And here is the link to the preview of the chapter 5 of the comprehensive Abaqus package. In this chapter, I have explained how to define transition zones using two methods. Now I want to talk about the description of the problem of this tutorial. First, I want to talk about material definition. In the model presented in this tutorial, the soil consists of two layers, ballast and subballast. Using only two layers will not affect the generality of the tutorial and the explained methods. Here you can see the geometry of the soil and its dimensions. The first layer is ballast and the second layer is subballast. A part named soil is defined and partitioned into 7 regions, including 5 infinite regions and 2 finite regions, including ballast and subballast. Here you can see the infinite regions. This region, this region, this region, this region, and this region at the bottom of the geometry. As it is illustrated in this picture, all the upper regions are assigned ballast material and all the lower regions are assigned subballast material. According to this picture, wheels are modeled as rigid boxes. All the dimensions of the boxes are equal to 0.02 meters. According to this picture, the model consists of 4 wheels. All wheels and pattern types can be modeled using the same procedure. This distance must be large enough to avoid numerical errors or unreasonable results induced by the first and second wheels. Here we have the first and second wheels. All the wheels must move in parallel to the z-axis with a velocity of 20 meters per second. Time period of the moving load analysis is 1.54 meter divided by 20 meter per second, which is equal to 0.077 seconds. The simulation consists of 2 steps. In the first step, concentrated loads are applied to the wheels in a quasi-static manner and reach their maximum value. Wheels do not move forward in this step. The loading rate technique is used to speed up the simulation without loss of accuracy. As you can see, I have set the time period of this step equal to 0.05 seconds, which ensures us to have a quasi-static analysis. In the second step, wheels start to move forward with a velocity of 20 meters per second. Basically, defining the first step is optional. The simulation can be conducted even without defining the first step. And here is the link to the first part of the nonlinear dynamic analysis tutorial. Now I want to show you the explicit Abaqus model. This Abaqus file consists of 2 models. In model 1, the Abaqus explicit solver is used, and in model 2, the Abaqus standard solver is used. Here you can see the part named soil, and here we have the wheel. Also, you can see the definition of ballast and subballast. I have entered these values according to the paper. And here we have the assembly. And here we have the step settings. The first step, I have not used mass scaling because I have defined a small value of time period. Now I go back to the slides. Here you can see the field output definition of the first step. As the first step is less important than the second step, only 10 frames are requested for this step. But as the second step is important, 100 frames are requested for this step. And here we have one of the history output definitions for the first step. As you can see, the domain is set to set and the RP1 set is selected. Also, the requested parameter is U2, which is the vertical displacement. Basically, the vertical displacement is requested to visualize the vertical vibration of each wheel. And vertical displacement is requested for all the wheels from RP1 through RP4 in both steps. As the first step is quasi-static, only 50 points are requested for this step. And here we have one of the history output definitions of the second step. Vertical displacement is requested for all the wheels in both steps. As the second step is dynamic, 500 points are requested for this step to capture the vertical displacement of each wheel accurately. And here we have the last history output definition for the second step. And in this case, horizontal displacement of the third wheel is requested for step 2 to conduct post-processing. And to investigate the induced vibration to the ground due to the moving wheels, a set is defined from a node along the path of the first and third wheels, and vertical displacement is requested only in step 2. Also, to investigate the induced vibration to the ground due to the moving wheels, a set is defined from a node near the path of the first and third wheels, and vertical displacement is requested only in step 2. Also, general contact is defined to account for all the contacts in the model. And according to the reference paper, frictionless interaction property is used. Now, I'm gonna show you these settings in the Abaqus. Here is the field output definition for the first step, and here is the field output definition for the second step. And here we have all of the history output definitions, and for first wheel, for the second wheel, for the third wheel, and for the fourth wheel. And as you can see, all of these have the same settings. Also, we have other history output definitions. Now I want to show you node 1 and node 2. I show the native mesh, tools, set, manager, node 1. This is node 1 along the path of the first and third wheels. And here we have node 2. And here I have defined frictionless interaction property, and I have used it in the contact definition. Now I want to talk about load definition. It is supposed that a concentrated force with the value of 2500 newtons is applied to each wheel. Here we have the load definition for each wheel. As you can see, the vertical component is equal to minus 2500, and as you can see, I have assigned linear amplitude to its definition to apply the concentrated forces in a quasi-static manner. At time step equal to 0, the amplitude is 0, and in time step equal to 0.05 second, the amplitude is equal to 1. So concentrated forces according to this curve will be applied to the model. Here is step 1 and here is step 2. Now I want to talk about mesh generation. As the wheels are rigid boxes without any curved faces, each face is meshed using one element. Here we have the second reference paper. This paper explains how to select the element size for the soil to have an accurate simulation. To decrease the simulation time, in this tutorial, the mentioned explanations are not implemented in the meshing of the soil. This will affect the accuracy of the obtained results, especially in the high-frequency domain. Here we have the mesh of the soil from the XY view. And as you can see, bias method is used for these edges to decrease the number of elements along the Y and X axis. And here we have the mesh of the soil from the YZ view. Now I want to compare the element size of the wheels and soil. To have an accurate contact simulation, the element size of the contacting face of the deformable part must always be smaller than the element size of the contacting face of the rigid part. And as you can see, here we have two elements in this direction and also two elements in this direction for the soil. Now I want to show you these settings in Abaqus. I go to the load module. Here we have the load definition for each wheel. And I go to the mesh module, and here you can see the mesh of each part. In the second model, the dynamic implicit step is used and two dynamic implicit steps are defined. All the settings of the implicit model is similar to the explicit model. Only steps are changed from dynamic explicit to dynamic implicit with the same time periods. Now I want to compare the runtime of the explicit and implicit models. The runtime of the explicit model is only 218 seconds, and the runtime of the implicit model is 39,071 seconds. And this curve explains that by increasing the number of elements and nodes, if the implicit solver is used, the simulation time increases in a nonlinear manner. However, if the explicit solver is used, the simulation time increases in a linear manner. Hence, for each model, by conducting mesh refinements, after a certain point, using the explicit solver is more economical than using the implicit solver. Now I want to compare the explicit and implicit results. Here we have the von Mises stress contour of the explicit and implicit simulations at step 2 and this step time. And as you can see, the stress intervals are similar. And this difference is completely natural between two solvers. And here we have the comparison of the von Mises stress contours at the start of step 2, which is the end of the step 1. And also here, the stress intervals are similar. In this figure, we have the comparison of the vertical displacements for node 1 based on explicit and implicit simulations. The blue curve belongs to the explicit simulation and the red curve belongs to the implicit simulation. As you can see, they are similar. And both the curves include numerical noise. Also in this figure, we have the similar comparison for node 2. The red curve belongs to the explicit simulation and the blue curve belongs to the implicit simulation. Also, in this case, they are similar and both the curves include numerical noise. Also, in this figure, we have the comparison of the vertical displacement for the third wheel based on implicit and explicit simulations. The pink curve belongs to the implicit simulation for the third wheel, and also the green curve belongs to the explicit simulation for the third wheel. Also, as you can see, they are similar. Here we have the comparison of the vertical displacement of node 1 based on explicit and implicit simulations, but the horizontal axis of the curve is the relative distance of third wheel and node 1. Here, as you can see, at the start of the simulation, the relative distance is minus 0.4. And when the relative distance is 0, we have this point. And when the relative distance is 0.4, we have the second point. And the difference of these two peaks are 0.4 meter, which is the distance between wheel 1 and wheel 3. And in this figure, I have used Butterworth filter with the cutoff frequency equal to 1000 Hz to filter the vertical displacement of node 1 based on explicit simulation. Here you can see that the numerical noise is removed. And only we have small oscillations here. If you decrease the cutoff frequency, also you can remove these oscillations, but it will decreases the accuracy of the curve. So I decided to use 1000 Hz for cutoff frequency. And in this curve, we have the comparison of the filtered and unfiltered results. The pink curve belongs to the filtered result and the blue curve belongs to the unfiltered results. And as you can see, they are similar, and the pink curve is approximately the average of the peaks of the blue curve. Now I want to show you the simulation results in the visualization module. I go to the visualization module and I set it to the explicit simulation and I hide the mesh. Here we have step 1 and then we have step 2. As you can see, the wheels are moving. And I go to the implicit simulation. Here we have step 1 and then we have step 2. And here we have the history outputs of the explicit simulation and implicit simulation. And for example, I save this history output U2 node 1 explicit. Here we have it. Now I want to apply filter to it. I go to create XY data, operate on XY data, and I want to use Butterworth filter. I select the data and I set the cutoff frequency to 1000 and plot it. Here you can see the result. And for example, I decrease the cutoff frequency to 500 and plot it again. As you can see, the numerical noise is decreased. I decrease it again, so you can see the curve is changed. Okay, the curve is changed. And I save each of them. This is U2 node 1 explicit 250 Hertz. I set it to 500, plot it, and save it. U2 node 1 explicit 500 Hertz. And I set it to 1000. Again, U2 node 1 explicit 1000 Hertz. Okay? And first, I plot the unfiltered result, then the others. Here you can see the difference. And I go to the first of all, I set it to inset and move it here for better illustration. And then, for example, I change this one to blue. It is U2 node 1 explicit, and this one, for example, I change it to red. It is correct. Also for the pink one, and for this one, for example, I use green. This green. You can see the difference. The best one is 1000 Hertz. According to this tutorial and the reference papers and Abaqus documentation, both the Abaqus standard and Abaqus explicit solvers are capable of simulating the structure response under moving loads, and in medium-sized and larger models, using the Abaqus explicit solver is much more economical than using the Abaqus standard solver, and filters implemented in the visualization module can be used to remove the numerical noise presented in the results. By choosing the cutoff frequency appropriately, the accuracy of the results will be preserved. Also, you can purchase the complete package of this tutorial. The complete package includes CAE, JNL, and IMP files and reference papers, a step-by-step tutorial about creating the explicit and implicit models, including detailed explanations. The package specifications and payment details are provided in the video description. 50% discount codes are announced on our Abaqus Telegram channel and official LinkedIn page. Their links are provided in the description below the tutorial. And here we have the link to the preview of the comprehensive Abaqus package. It includes step-by-step tutorials, and it includes 39 hours of instruction from beginning to advanced level of using Abaqus. Also, it has mechanical and structured subpackages for mechanical and civil engineers. You can contact us using Telegram or WhatsApp, or you can send email to us. We can have one-on-one tutoring on the AnyDesk WhatsApp, and we can make special tutorials to your order. We can conduct high-quality simulations for your thesis, exercises, and industrial projects, and we offer support in writing the modeling and result discussion part of your thesis, and we have consulting services for MSc, PhD positions or job interviews, and we can help you to prepare the presentation of your simulation works. Now I want to suggest you several related videos of our YouTube channel. Thank you so much for watching this video. Have a good time. Goodbye.